In this video, we'll take a look at how to make a post-process effect in HLSL in Unreal that emulates a low-quality video or glitching camera type effect. To do this, I'll introduce how to create effects like pixelation, blur, channel separation, and buzzing. And in combination, use those effects to produce a result like this. We'll also be taking a look at how to automatically apply this effect to our gameplay camera, which will go over how we can create and utilize render targets through blueprints. To begin, we're going to start with a game template, and the template we're going to use is a third-person template. You can use your own projects, but I'm going to use this as an example so that we can actually apply this effect to our character's gameplay camera. So I'm going to go to Games, Third Person, and create my project. And I'm going to call this post-process underscore glitch. So once the project's created, if we click play, this is kind of what we end up with the third person template. And in our last video, when we did the Sobel edge filter through HLSL and applied that as a post-process, we just applied that manually to our post-process. But this time we're going to do it a little bit different, because if you wanted to make this into an actual game or have it apply that effect when you click play and are spawned and looking through this third person camera, we have to set that up in our blueprints. So what we're going to do is go down to this third person folder here. We're going to go to blueprints. We're going to open up our BP third person character blueprint. This is our blueprint for our character. So if we go to viewport, we can see that we have our character, the camera behind it that got spawned when we play is connected by this camera boom or spring arm component. What we want to do is take this camera and through blueprints dynamically create ourselves a render target that will fetch whatever we're viewing through that camera as an image, run it through our material, which is going to do the distortion effects to that image, and then display it as our post-process effect. So that's what we're going to want to do. And this will be more suited for if you were making a game where you want that effect properly applied through gameplay. So we're going to go to the event graph here, and normally this is where all the event begin play starts, that sets up all the player controls so we can move that character around. We're just going to space this out quite a bit and give us some room here to add our node network, which is going to, again, create a render target, which will pretty much be fetching what we see through the camera and storing it as a texture. And then we're going to take that texture, run it through our material, which is going to distort or modify that image. And then we're going to apply that material to a post-process. So we see that as our result. So the first things that we're going to have to do is we're going to want to add a post-process to this blueprint, as well as a scene capture component 2D. So up here, I'm going to go add, and I'm going to search for a post-process. And then we're also going to add a scene capture component 2D. So you can see that this says used to capture a snapshot from a single plane and feed it into a render target. So the reason why we're doing this, and maybe this isn't too important for what we're doing in this video, but if you wanted to capture multiple frames or offset frames and blend them together, you'd need a way of capturing that frame. And you could do that through this. You can capture what the camera is seeing and store it essentially to a texture that you can use. So I'm going to use this scene capture component 2D, and I'm going to move it. Actually, I don't think it really matters where we have it exactly, but it's going to probably want to be under the camera. So we're going to put it under our follow camera here and have our scene capture component 2D. And as soon as we do that, one other thing that we'll want to do is for our post-process, we can click compile up here. We want to go on our post-process and just make sure it's set to unbound, so it affects everything, not only things within the square wherever it's placed. So just make sure it's set to unbound. Now what we're going to do is create our render target. So we're capturing what the scene sees, or what the camera sees, through this scene capture component 2D. We need to now store that result somewhere. We need to store it into a render target. But we can't manually create a render target in our content browser because it would require us to specify the width and the height, but that's going to be dependent on the gameplay and the settings of the game. So we want to set that dynamically through our blueprints. So what we're going to do is we're going to drag out this event begin play, and we're going to create a render target 2D. There we go, create render target 2D. And you can see it asks us for the width and the height of that texture that's going to store whatever we capture through our scene capture component here. And we haven't hooked that up at all yet, but we will. But how do we set this width and height? There's a couple ways. We could do get viewport size, and then we can fetch the viewport size. And then the return value doesn't connect to these, so we can split that and then connect it. But I'll have to do a conversion because this is storing it as a float or a number with a decimal place and additional numbers, whereas here it's just looking for whole numbers or integers. So this is one way that should work, but maybe a better way to do this would be that we get our camera that we're playing through, so we can do something like get player controller, and then get viewport size. And then we have size X and Y that we can connect up with no conversion. So maybe that's a better way to go. It should produce the same result, but we'll stick with that for now. So now we're creating our render target with the proper width and height of our screen or whatever we're playing through. The next thing we have to do is create this render target or store it somewhere so we can use it and assign it to other things. So whenever it's returning, the render target that's returning here, we're going to right click and promote to variable. And now you'll see it get added down here. And now that we have it in our variables there, we can give it a proper name. So maybe I'll call it capture frame. And there it is. And now it's setting. This is pretty much our render target that was created here. So now we're able to use it. So the next thing that we're going to do is go over here to where it says set, and we have our capture frame, our render target. We're going to drag out the bottom pin here, and we're going to do set texture target. And maybe I have to turn off context sensitive here, and there is somewhere set texture target for scene capture component 2D. So that one. And now it's going to set this texture to be the render target for our scene capture component 2D. But we have to connect that up. Right now it's saying set, but where's our target? Where's the thing that we're setting this render target from? Where's the scene capture component that we're using to feed into this render target? Well, we don't have it connected right now. It just says self. So we need to connect that. So we're going to take our scene capture component 2D and just drag and drop it into our network here and connect that up. So now we're taking whatever our scene capture component 2D sees, and we're pretty much taking that image, storing it within our render target, which has a width and height size of whatever our camera or viewport size is. So now we're successfully storing what we see through the camera into this render target 2D. So now that we have that, we can start making our material and maybe test this out before going too much further. So we're going to compile, save, and just minimize this for now. We're going to go back to our content browser and make a new material. So I'm going to make a material, and this is going to be our material that does all of our effect generation. It's going to do all the manipulation of that image. So maybe I'll call it m_bitrate lossy, and that will be our post-process material. We're going to open up that material, select that material here, make sure the material domain is set to post-process. We're also going to scroll down to where it says blendable location. This is where this gets applied throughout the post-processing steps. We're going to set it to scene color before bloom, which should give the result that we want, but you can always play around with that later on. So you can always change it, but that's what we'll go with for now. And then we're going to create our custom node, which will do all of the kind of distortion effects and all the effects on our screen's image. And we're going to connect that up to our emissive color. And you'll notice that I'm using Unreal 5.4, the latest version of it, which now has this little code box whenever you create a custom node, which is really nice. So that's why we see that now, which is great. And in here, I'm going to add 2 inputs to our custom node here. The first thing we want to input is our UVs for our screen. The second thing that we're going to want to input is our texture or our render target that we're going to be using. So for our UVs, we're going to create another custom node like we've done in our kind of last videos, where we're going to use this custom node to get the UVs of our screen or of our viewport. And this is a built-in function to Unreal. You can just return get scene texture UV parameters, and that's really it. Just make sure that this custom node is set to a float 2 because it's UVs, U and V, 2 values, not 3 values. So float 2, and it should go yellow, and then you know it's working. And then for our texture, this is going to be where we're going to feed our render target into, which we'll be doing through blueprints, but we need somewhere to connect it in to our custom node. So we're going to drag out this text here and create a texture object. Texture object is going to work, put into our custom node. A texture sample would not. So we want to make sure it's a texture object. And it has a default image there that it uses. We want to make this a parameter so we can access it or change it from outside this material network. So we're going to also right click on it and convert it to a parameter, and we'll just call it RT for render target. And that's really it. And what we want to do in our code now is just return this render target just to make sure that everything is working. So what I'm going to do in here is create a float 3, and it's going to be called frame capture, and it's going to be our texture 2D sample text sampler, and then use our UVs, and we'll just return that frame capture. So that's really all we need to worry about for now. We'll save this, and we're going to go back to our third person blueprints BP third person character, back to our event graph here where we're creating our render target. And now that we have that material to work with, let's try applying this render target that we're creating to that material, and then have that material attached to our post process here. So how are we going to do this? Well, what we're going to do is go in here, and after we've set our capture frame render target to have whatever is being captured through our scene capture component 2D, we're going to apply that to our material that we just created. So we're going to drag this out, and we're going to create a dynamic material instance. And what we're going to do is the parent, the material that we're going to be creating an instance from, is going to be that M underscore bitrate lossy material that we just created. And then what we're going to have to do is set that parameter that we had from that, the RT parameter, the render texture parameter, to use this render target here, this capture frame render target. So before doing that, we're going to create this, and then for the return value, we'll also promote that to a variable. So we're going to promote the result of this to a variable, and we'll get a new variable down here, and this will be our material. So I'm just going to call it bitrate lossy instance, and we know that that's our M underscore bitrate lossy material, the instance of it, the instance that we're creating. So that's what we're going to want to do. And then what we're going to want to do is set the parameter of that instance, that RT, that render target parameter, to have this capture frame plugged into it as a texture. So normally, just so this makes sense, normally if you have your material and you create an instance of it, create material instance, you have whatever parameters you exposed. For example, we have that RT parameter that we could set to any texture that we want. You know, I could change it and it changes. We want to do that through blueprints. So instead of manually creating that instance, I'm just going to delete this. Instead of manually creating that instance, we're doing it through our blueprint here. And then we're going to set that RT parameter to be our captured frame. So very easily we can do that. Right after the set here, we're going to do a set texture parameter value on our material. And our material is this dynamic material instance that we created here. So we just connect that up, our bitrate lossy instance, which is the instance we just created. The parameter we want to attach something to is that RT parameter. And the value, the thing that we want to plug into that RT parameter is our capture frame. So we'll drag in the capture frame, get capture frame, that's our render target, connect it to what we're plugging in to that render target parameter. And now we've essentially assigned it to the instanced material. So now this result here is our instanced material with the render target plugged into that RT parameter. So it'll just return whatever our screen currently sees. Now, how do we actually attach that to our camera's post-process? If you remember, again, in the previous video, we had a post-process in our viewport here, you know, post-process. And we went under to where it is material and went to post-process materials and added an array, set it to asset reference, and plugged in our post-process material. We want to do that process through blueprints. So how do we do that through blueprints? Well, I'm going to have to give myself a little bit more room here. But after we set our texture parameter value, I'm going to drag this out and I'm going to set members in post-process settings. And then what we're going to do is get our player character. So get player character. And then get component by class. The class or the component class is going to be our camera component. We want to get the player's camera component, right? Then what we're going to do after we get that camera component from the player character is we're going to return that as what we're setting the post-process settings for. And I can't really connect this up. Like it says, you can't do that. But we actually can do this if we go here to this set members in post-process settings. And if you look at your details when selected on this node, you have things that you can set for pins for a bunch of options here. And essentially all we want to do is pretty much all the settings. So we can go here and we can go and drag out our get component by class, the return value, and we can search post and we can go and get our post-process settings and feed those settings into here. And now it's going to set all those settings. And then what we're going to do is drag out the setting that we want to modify. So saying that we want to modify from these post-process settings is the post-process materials. So I'm going to go in here and search post-process materials. There it is, post-process materials. I'm going to check to create it as a pin. Now we have a new pin called post-process materials. We're going to drag that out. We're going to make weighted blendables. That's essentially the equivalent of when you click on that and add an array. So that's what we see here, array. And we're going to make an array. And then our array is going to be connected up to, again, make weighted blendable. This blend amount is how much it's affecting it, so we're going to set it to 1. And the thing that we're connecting to our post-process materials is going to be this object here, which is going to be our material, which is what we have here, this bitrate lossy instance. And we'll drag that in, get it, that's our material, the instanced one with the render target texture assigned, and we're going to plug that in there. And that's it. And by doing that, we've pretty much done all those manual steps that you might normally do, but we've done it all through blueprints. So now that we have this done, we'll connect this back up. I'll move all this back over here and just connect the output to continue setting up the player controls and all that, just like that. And that's it. And we're going to go give this a try. I'm going to compile, save, minimize. I'm just going to expand my viewport for now and click play. Does this work? Okay, my camera looks a little bit messed up. Why is that happening? Play. Did I move my camera? Let's go take a look. Viewport. I did something wrong here. That scene capture component, I never moved it to where my camera is. So it's just capturing like a totally different area, but it worked. So take a look at this. If I put it where the face is or the head is right behind it, and I click play, now what we're seeing is not actually where our camera is where that scene capture component is. And this is all working. So it's essentially the equivalent of just moving the camera, but we're actually getting our result from the scene capture component here. So what I'm going to do is I'm going to move these cameras to match up perfectly. We can just eyeball that in or actually properly match it. I should properly match it. So I'm going to go here and look at this actual camera's location. And I'm also going to look at its field of view. And I'm going to take our scene capture component and make sure it's the same field of view and at the exact same location. Just reset it all to 0. And that's it. And I'll click compile, save, minimize, play. Wow, that's all working. Now, how do we know this is actually working? Well, we're going to go back to our material just very quickly. Our M bitrate lossy material. Let's try inverting the colors. So I'm going to invert, or it's 1 minus in Unreal, 1 minus our result, whatever we're capturing from the frame, and save that. And now let's click play and see if that actually works. Are we actually seeing that camera view be affected by our material? We are. So there we go. Now everything's inverted. So what we're doing is we're creating a render target, capturing our camera's view, storing it to that render target, applying it to our material here as an instanced material, and then applying it to our post-process, all through blueprints. So now in our viewport, everything looks normal, but when you play, it does that whole process, and we get our result. It runs this material and attaches it to the post-process of our player's camera. So that's all good. So we kind of briefly talked about what we're going to have to do to make this effect. If I just quickly think about it, like what makes a low quality video effect or kind of like data moshing effects? What are things that you can do to produce these kind of results? There's plenty of things. You could streak pixels based on the camera movement. You could capture the before frame and after frame and blend them together in different ways. But we're going to start looking at ways you can start producing these kind of effects. So the 3 things that come to my mind, just really quickly thinking about it, would be, first of all, with low quality or low bitrate effects, you might get some blockiness or pixelation happening. You might also get some color banding, lower bit depth, less colors representing your image. And then possibly also poor connection artifacts. This could be buzzing, or it could be jittering edges or poor anti-aliasing, but you want some sort of maybe connection artifacts, a blurry offset kind of result, something that makes it feel a little bit low quality or distorted. So let's try these three things: blockiness and pixelation, color banding, and then poor connection artifacts, or even color separation, like the color channels separate to give it like this chromatic aberration type effect. So let's see how we can do these three things. First thing we're going to start with is the blockiness and pixelation. So let's think about how we can make this pixelated normally, not through our post-process material. I'm just going to move this over here and set this to just temporarily. I'm going to set it to a surface. I'll drag out a texture sample, and I'll load in just very quickly logo here. There we go. How can we make this image more pixelated? Well, what we can do is take the texture coordinates and modify them. So if I take the texture coordinates and I view them, there we go. We got our texture coordinates going from 0 to 1. What happens if we multiply that? Well, if we multiply that, it'll become brighter. It'll go from 0 to whatever we multiply it by. So maybe something like 256. Preview that, everything gets way brighter. Now what we can do is use something like a floor, and I'll round it down to the lower integer. Won't make much of a difference now, but if we do that, and maybe this value here will make a constant so we can control it, 256. If we divide this result by that value, and we preview this, it looks the same, right? But it's really not. If I zoom up really close, and maybe this number is still too large to really see, but it's actually clamping the color from 0 to 256 in each direction. And we can maybe see this better if I put this number lower. What happens if I go to 128 or 64 or 32 or 16? Now you start to see those squares. So normally it would be like this. It's whatever the texture resolution is. But by multiplying it, flooring it, and dividing it, we can clamp it and choose how many colors or pixels we want from the resolution. So it's doing 16 by 16 blocks of colors. So if I use that as my UVs, we're pretty much just clamping the UVs to be a specific number of blocks in X and Y. So we're modifying the values. If we use that as my UVs, there we go, everything's pixelated. If I do 32, it's 32 by 32 pixels or blocks. Now it's a bit less. What about 48, 64, 128, 256? So now we have a way of easily modifying the UVs to produce a blocky effect. So how can we do this through shader code? Well, it's pretty much the same thing. Take our texture, multiply it by value, floor it, and then divide it. So let's go do that. So I'm going to put this back to our post-process, connect it up. There we go. And we're going to go to our code here, and we're going to do that whole process. So I'm going to jump into Visual Studio Code with our same code that we currently have right now. And we're going to do what we just did through nodes, through HLSL code. It's going to be really easy to do that. So all we're going to do is we're going to start off with, I'm going to type in here, blocky Pixelation Effect. We're going to have some parameters that we can adjust. So first of all, we want to have a parameter or float, like a variable for our block size or scale. Maybe block scale is a better word for it. And it'll be 150 we'll start off with, so fairly pixelated, just to see if it works. And then we're going to make a float 2 called block UV. These are going to be the distorted UVs that make things blocky. And then we just do what we did through nodes. We take the floor, or we floor the UV times our block scale divided by block scale. That's it. That's our blocky UV effect. And then we make a new result with that effect applied. So float 3 will be our block result, our pixelated result, which will be our texture 2D sample. Sample with the texture that we have plugged in, which is our render target, and we'll make it just a normal texture load here. And then instead of UVs, normally we do UV, we do our block UV, our modified UVs to make it blocky. So that's really it. And then we're just going to output that result instead. So we're going to return our block result. And we'll take this, throw it into our code here. So I'll throw it in here. No errors, save, play. Does this all work? Let's find out. If I click play, yeah, everything's super blocky now. So we got our pixelated result. Great. So what can we do next to make this better? Well, now that we have the blocky result, what if we want 2 different levels of blockiness? This will help it feel a little bit more kind of low quality or lossy, like when you have low video qualities or low texture qualities and the bit rate isn't fast enough, you get these blocky areas appearing. So maybe a cheap way of doing that, or a really easy way of doing that, just simply, is we're going to have 2 different block scales. So maybe we don't call it block scale anymore. We call it block minimum and block max. And we make one maybe 100, another one 300. Okay, so we're doing 2. So we're going to modify this. Instead of block UV, we'll do block UV min and block UV max. And then change this so instead of block scale, it's block min and block max. And we do that for both of these. So now we have 2 things. Our minimum block UVs, our maximum block UVs, both using these different values. And then our block result will have 2 results. Block result min, block result max. And again, I'm keeping this very simple. So now block UV min, block UV max. And instead of just returning one of those results, we're going to blend 2 of those things together. We're going to do a lerp, which is like a mix. So we're going to blend our block result minimum and our block result maximum by 50%, 0.5. So half of this, half of that, it'll overlay them. So we'll take that and we're going to throw that back in here. No errors, save, and let's play that. Okay, so now we have 2 different levels of blockiness being overlaid. And that maybe looks a little bit more interesting because you see the blocks kind of overlapping and it feels just more like they're popping and it produces a different type of effect. So I think that's a little bit better. So now we have something even better. And this is our kind of pixelated effect. We've pretty much done that really easily. So maybe what we're going to do now is add a bit more complexity. It might be nice for when there's fast movements, it becomes more blocky. Like the bit rate or the quality can't keep up with quicker movements, so it becomes more blocky as it buffers or loads or something. So to do that, we're going to add another variable to our custom node. We're going to add another variable here, or input, not really variable, but an input that will produce a variable, but we'll add an input called velocity. So I'm going to go here, click on our custom node, add another input, and this new input is just going to be called velocity. And there it is. And we're going to connect that velocity to a SceneTexture node, which can fetch the velocity of our scene. So just quick movements. So we're going to take the color and put that into our velocity here. So now this variable called velocity will store the speed of movement in red and green, in X and Y. So that's what this will be. And to test to make sure that works, we'll do a quick modification to our code. Instead of blending block min result by block result min by block result max, we're going to blend block result min by velocity just to see if this works, velocity. And that's our new input that we just created. So I'll paste that in here just to make sure everything works. And we'll save that, minimize this, and click play. And now when I move, look at that. You see those colors that it generates on quick movement. This all seems to line up and work. When we look at our character, where those colors are, that all seems to work. One thing that you might run into an issue with is if you resize your viewport to like a strange size, like really wide like this, and I click play, see how it's all offset? And now when I move, everything's totally wrong. This has to do with, in our blueprints, how we're getting our viewport size. That doesn't really behave the best in the editor. So we're currently doing get player controller, get viewport size, and that doesn't seem to work the best right now. If you really want something that's totally fail-proof or safe for when you deploy your game or deploy your scene, one thing you could do, and I'm just throwing this in as an additional thing, one thing you could do is get the game settings, get game user settings, then get screen resolution, and then split this and plug that in, X and Y. And if you do that, it's like a fail-safe. This always works, at least from what I've seen, when you deploy your game. So a way we could test this is if you were to go here and just go up here to test it in a standalone game. When it launches that standalone game, this will all behave as expected, even though in the viewport scene that we see right now, it might not look correct. So that way you'll actually get the game settings. You can see here it's loading. Once it loads, once it plays, you shouldn't run into any issues with that approach. See how I move here, it all lines up perfectly. So that's kind of what we want. So just as a note, if you deploy and something's not working, that could be your ideal solution for it. But for now, I'm just going to use what we previously had and just make sure that when I click play, I have my viewport sized up and not squished to a weird offset. There might be other ways to fix this as well, but this is just something you might run into. So if I go selected viewport, you know, if this is all the way down, then it works correctly. And again, all of it has to pretty much fit your whole screen for it to work. There we go. So just wanted to cover that in case you run into that issue and you're going crazy wondering why that's not working. So back to our material. So we have our velocity now. It is working. We could see that it's returning the velocities. We're going to use that velocity to produce a mask, a movement mask. So what we're going to do is let's go back to our code here, just so you can see this a bit easier. And we're going to make a movement mask where darker is less movement, brighter is more movement. The easy way of doing that is we can go here, create a float, call it velocity mask, and we're going to make it take our velocity red and add our velocity green, both together, and then times it by like a multiplier by 10. And as you increase that multiplier, it would create the effect to be more pronounced. So we'll do that for now. We'll do the same thing, blur our block result min. Instead of blurring it by velocity, we're going to switch this around a bit. We're going to blur our block result max by our block result min. And the amount we're going to blur it by is going to be our velocity mask instead of 0.5. So velocity mask. And we'll want to clamp that velocity mask to make sure it doesn't go to negative values or values over 1. So we'll do a clamp velocity mask by 0 to 1 range, and that's it. And we'll take this, put this back in here, save it, minimize, and click play. And what do we get? Everything's kind of not as blocky, but if I move quick, then those more blocky values show up. You might not see it too much here. So maybe what I'll do is I'll go and increase the exaggeration of that. Instead of multiplying our velocity mask by 10, I'll multiply it by like 100. And I'll just save and try that out to see how that works. So if we click play, now when I move quickly, things become more blocky. Might not be too easy to see here, but you can see when I move forward, the ground becomes more blocky because that movement mask kicks in. So now we have controllable blockiness based on our velocity. So let's go back now and clean up our code a bit. Instead of just multiplying it by 10 or 100 here, I'm going to make another variable called velocity sensitivity. And I'll make that a new variable up here and just set it to maybe 100 was good, but maybe a bit extreme. I'll set it to 75. And for our block min, maybe I'll do 50. And for our block max, maybe we'll do 800. And we should probably start commenting some of our code as well. So I'm going to remove this. I'm going to call this sensitivity of velocity and min and max pixelation effect. So just some quick comments so we don't get lost in our own code. So maybe this is min and max block coordinates for pixelation effect. And then down here, we have our image slash frame with min and max block sizes. And then down here, we have our sum of our red and green channels to produce velocity mask. So just adding the masks, creating the mask by adding the different movements both together. And then we multiply this by our velocity sensitivity to control the intensity. And then finally, we return our result. So maybe it'd be good now that we have our final pixelated result with the blending based on our movement. So maybe what we'll do is we'll make a new variable float3 called result pixelated. And that's going to be the result that we have. There we go. And now we can just return that at the very end. Just trying to keep our code organized at the different stages. So that's our resulting pixelation effect, blending the max and min pixelation by clamped velocity mask. There we go. So that's our code. So I'm going to take all that, throw it into our material just to make sure it's all the latest code that we have here, save it, make sure I didn't type anything wrong, and we're all good. So perhaps the next thing to make this look more low quality is to limit the color range or the bit depth, or to quantize the colors, to limit them. So we're going to go back into our code and we're going to make a function. So I'm going to go at the very top here. I'm going to make a function to limit the color range. So it's going to take our resulting image and pretty much take the colors and throw out everything that doesn't snap to a certain range, or that isn't within a certain level of colors or a certain number of colors. So we can do this through a function, and I'll create a structure to hold that function. So I was going to create a struct glitch effects, and maybe I'll call it glitch effects. I'll call it glitch when I want to access it. And we'll make a function called quantize. It'll take an input, which is our color, and then we'll specify a range, how many colors to allow to be used. And what we're going to do is we're going to specify a step size. So this is how it figures out pretty much the size of the color step. So we take 1, divide it by our range, whatever we input, minus 1. So I'll just add a comment here. So this is going to be size of our color step, and that's based on our range. So 32 will be like 32, lower quality than say 128 or 256 or something higher. Next thing we want to do is we'll want to take that step size and round our color, or our input. We're going to take our input color and we're going to round it to fit within that step size, how many colors are allowed to be used. So essentially it'll make things that are gradients or bright areas that are going from shadow to bright or something, it'll make them a lot more blocky and have a less color range. Like it'll pretty much make them look like a low quality bit depth texture. So to do this, we're going to pretty much modify our input. So we're going to modify our input to match the nearest color step. And we'll do this by making a float 3 called quantized. We'll round our input divided by our step size, multiplied by our step size. And then we'll return that. So we're going to then return the result and return quantized. That's it. That's all we need to do. And we can now use this function. So at the very bottom here, instead of going and returning the result pixelated, we are going to return our quantize function. So glitch.quantize. That's our input, our result pixelated. How many bit range do you want to use? Let's do 8. Let's make it really low quality. And let's take that, throw that into Unreal. Any errors in my code? Oh, look at that. You can already see here. It's quantized. It's all low quality color depth. And if we click play, how does this look? Oh, it's horrible. It's just terrible. So maybe that's a bit too low. Maybe I went a bit overboard there, making it 8. Let's try setting that to 64 or maybe 128 and save that. A little bit more color range. And now if we click play, okay, that looks good. And then if we go to these darker areas here, see how the color is low quality, limited range? That's the effect that we want. Now, if you are subscribed to the Patreon that you can find in the description below, I'll also go over how you can do that quantize effect directly through nodes in Unreal. I'll show how you can do that for that as well. But since we're wanting to save time for this video, I'm not going to go through that here. But you can find that if you're part of the Patreon in the PDF. But the next thing that we're going to do now that we have this code is you'll notice everything gets super, super blocky. We want to add some blur to our pixelated result. We want to blur it a little bit, and that's really going to tie it together and make it feel low quality. Right now it feels too sharp. So how can we do a really cheap blur? There's a bunch of algorithms for blurring that get fairly complex, but let's just approach it in a really, really simple way. So I'll also show you how you can do this directly through nodes, but again, to save time in this video, I will just be doing it through HLSL code, but again, it's in the PDF if you're interested. But we're just going to jump back to our code here, and we're going to do a blur. And the very cheap and easy way that we're going to do a blur is we're going to specify a couple levels of blur, two values for different blurs, maybe one that's maybe not as strong, one that's more strong, and then we're going to blur our images by offsetting the pixels to the top, bottom, left, and right, and adding all the results together. So essentially, we're going to take our frame, our resulting image, we're going to offset the pixels in each direction by a specified amount that we can change, and then we're going to add all those results together, and that will be our blurred result. So it sounds a little bit weird, but it's pretty much a very simple like blur by doing just simple accumulation of our image, or adding our image together a bunch of times with a bit of an offset. So before I dive in and go over this blur, I'm just going to set this quantize amount to 256. I think that would be good. 128 is still even a bit low. So I'll just leave that for now. And in between here, right below our result pixelated, that's where we'll start adding this part, this next section. So what do we need to do to make things kind of blurred? Well, first of all, we need some blur values. So that's the thing that we really need to have first. And to do that, we're going to create a float 3. We're going to create a temporary storage just for the blurred result. So I'll call it result blurred, and I'll just make it hold nothing for now. And now we want to have all our blurred results together. But before even doing that, I'm going to want to have, actually even before this, we're going to want our offsets for blurring. So I'm going to make a constant float 3. They're not really changing as we play, so I could just set it as a constant. And I'm going to call it blur offset. And I'll make it a float 3, but really it's just going to store 2 values that we're going to use. Over and over again, we're going to be using some of these values. So this will just be an easier way. And to make these values, you could type 0.01 or 0.1, or you could just do 1 divided by 1024. I find that a little bit easier to just turn it into a division. So you're dealing with larger numbers, but you can really set this however you want. It could be point values, or you could just do what I'm doing here, 1 divided by whatever you want the blur value to be. So I think this will be an easier way to think of it. These are going to be your 2 different offset values. You could play around with them after and see their result, but I'm just going to start with this. And then I'm going to have the third value just be a 0. So there's our blur offset values. This is X, Y, Z, or RGB. We're just storing 3 different values in a single variable. And then we're creating our result here. So I'm just going to add the comment in here, placeholder for blurred result. And then what we're going to do is use these offsets to offset our UVs as we just keep adding the image together with different offsets. So to do this, we'll do a comment here. We're going to accumulate our results. So we're going to do result blurred plus equals. Right now it has nothing in it, but we're going to add our result pixelated. And then what we're going to do, result blurred, I have to do this a bunch of times, so I'm just going to copy that. Next, what we're going to do is do a texture 2D sample. We're going to take our texture, so text sampler. We're going to take our UVs, our normal UVs, not our blocky ones, because we're just going to want to blur our normal image and overlay it. You could use your blocky ones as well, but I think this will give us a more kind of blended result. It might help, but you can try it with the block UVs. But let's try this first. And I'm going to take those UVs and offset them. So I'm plussing an offset, and by plussing an offset, I'm adding a offset to the right, and or however you look at the UV space. But let's say to the right, and I'm going to call this our blur offset. We're going to use one of these values. So blur offset X. We're going to use this as our offset in X, and then in Y, we're going to offset it by 0. No offset in Y. It's only offsetting to the right. To the right, because we're plussing this value. If we're minusing it, it would be to the left. So we're offsetting it to the right in X by this value, and in Y by 0, or I could do blur offset dot Z, the third value, X, Y, Z. I could also put 0 in there, but maybe this is better. I can even get rid of that 0 here and just use 0 instead, but it's all whatever you prefer. So I'll call this right offset. And I'm going to do this a bunch of times. So I'm just going to copy and paste this. Right, left, bottom, top. And now we're going to adjust all these. So the next one, we're going to offset to the left. So instead, it'll just be negative. Everything else stays the same. And that will be left offset. And then we want to offset up. So we'll plus, but this time it will be Z here, 0. And then for Y, it will be Y, this other value. And that will be up offset. Or actually, since that's plus, would that be up or bottom or down? I don't know, maybe up. Actually, maybe down. So bottom offset. I'm trying to think of how Unreal looks at the UVs. And then this last one would be top offset, where we just flip it to a negative. So there we go. And this should be Z, and this should be Y. So that's it. And you can make these offset amounts the same. but depending on your screen sizing or depending how you want it to be, you could try changing it up. Sometimes having a more vertical blur might look interesting, or more of an offset in vertical space or horizontal space. You can adjust these. We'll try that out. And this is a really simple way to do this. But since we're adding this all together, like we're adding the image on top of itself 1, 2, 3, 4, 5 times, it will become super bright. So what we have to do is divide it or kind of normalize it. So we're going to divide by total accumulated. In this case, it's 5. So we're going to do our result blurred divide by 5. And that's it. And that should give us our blurred result. So let's just output this blurred result and nothing else. So I'm going to do return result blurred. Let's see what that looks like. I'll copy this, throw it back into Unreal. Any errors? No errors. Save. Minimize. Play. Okay, now it looks blurred. And when I move, you start to get that blocky effect. And you see it overlaying, but it's not as powerful as it was before. It's not as overpowering. So this kind of works pretty nicely. Now you can play around with this. You could try blurring your blockiness result, and maybe that works better. But I think this is pretty cool. So this is working pretty nicely. So let's go back to our code one more time right now, and let's quantize the result. So what we're going to do now is instead of just turning result blurred, we're going to do what we did before. We're going to return our quantize. So it limits the colors, but instead of returning the pixelated result, we're going to return the blurred result that we're going to quantize. So we're going to quantize our result blurred with 256 colors, and that will be what we'll use. And maybe we'll adjust some of these settings as well. Maybe I'll just go back up here, and for our block size minimum, I'll do 100, maximum 500. And let's make our sensitivity for movement 250, so it really kicks in when there's any movement. And take all this, throw it back into Unreal, save it, make sure there's no errors, and let's click play. Blurry, and then when we move, we get this kind of blocky effect, and we have all of our very low bit depth looking colors. So now the next thing that I think we're missing here, like this is looking quite low quality and quite low bit rate. It's kind of giving us that illusion. But maybe what we're missing is some poor signal effect or some buzzing or separation of colors. So let's take a look at how we can do that. So jumping back into our code. Now what we're going to do is start to add our very final segment of this, which is going to be some random buzzing noise or artifacts that separate the red, green, and blue channels of the image. So we're going to have to create a couple of variables, and we're also going to have to add an additional variable that we'll use. The additional variable that we're going to have to use will be time. We're going to use time from the game to drive a kind of fake randomized noise to help make our buzzing or our glitching effect on the edge of our pixels. So we're going to have to add that to our custom node, but first let's start setting up some of these controls. So I'm going to do a float for our noise scale. So we're essentially going to be adding noise to our image that's going to separate the color channels. So I'm going to make a noise scale. It's going to have to be pretty low. Something like that we can start with. And we're also going to make a noise speed. And all these could be adjustable, but we'll just block in some starting values. And then later you can always play around with it. And then what we're going to do is make our noise UVs or UV noise. And this will be our current UVs multiplied by our noise scale, which we set here. And then we're also going to do our time noise, which will equal our time multiplied by noise speed. So we have a couple of variables now. Our UV noise and our time noise. Time noise is our time multiplied by our noise speed. UV noise is our UVs multiplied by our noise scale. So one last thing that we'll need is also how much we want to separate the colors or the channels, like the red, green, and blue channels, based on this effect. So I'm also going to add one more control here called chromatic strength, and that'll be how much we separate the color channels. And again, these settings can be adjusted. So first thing, now that we have all these variables that we can use, is we want to create our fake noise. So we want to create a pseudo-random noise based on UV and time. So based on UV and time. And we've done this before, but we'll do it again. It's this float noise. We'll take fractional values of dot UV noise. We're going to start using these UV noise plus time noise. Float 2, we just create some simple random values here. You can really make these values whatever you want. You'll change the effect slightly, but I'll do 789101 multiplied by 54321 1 2 3 4 5. I'm not putting much thought into this. There we go. That's it. That should work for our noise. And I just minus 0.5 at the end, but again, we can adjust those. But I found like they'll probably give it a good value to start with. Sometimes you can -1 or minus other values, but you can just change these up. I could probably even get rid of that. Wouldn't make much of a difference. So the idea is I'm going to make 3 UVs, 3 separate UVs, UV red, UV green, UV blue. Each one of them are going to be offset slightly differently based on this noise. And then I'm going to use those UVs on our image and combine that all together and add it to the end result. So let's try this out. So the next thing is going to be apply our chromatic aberration. It's not really chromatic aberration, but it's like a cheap way of doing something that gives it that look. So apply chromatic aberration by offsetting UVs with noise. It's a very cheap way of doing this. Cheap meaning simple and also not complex. So we'll do our UVR, UVB. We can actually do this once and then copy and paste it. So I'll take the UVs, and again, we're just offsetting it. So float 2, but this time we're going to use noise and then 0 and multiply that as like a strength control by our chromatic strength. So if you change that chromatic strength, it'll make this effect more pronounced. And we're doing that for UVR, B, and G. UV R, B, and G. Red, green, and blue. R, G, and B. There we go. And we have to change these. So the first one will have noise in X. The second one will have noise in Y. And the third one will have noise in X. Something like that. And then what we're going to do is apply these UVs to our current frame or output. So to do that, float 3, color R, and we could probably simplify this, but I'm trying to do this in the most easy way to understand. That's why everything's like red, green, blue instead of like combining things or doing other ways of building this. But this will be our texture. So text sampler, we've done this many times before now. And we're just changing the UVs to be using these UVs for the red channel. And the key here is it's only going to store the red component, only be the red component of the image. That's why I put .r at the end. And we're going to use for red, green, and blue. So red, green, blue. UV R, G, B. Red, green, green, blue. That's it. And now we add all these together. So how do we add them all together? Well, very easily, we can make another variable, float3. I'll call it color chromatic, and it'll be float3 color r.red, color g.g, color b.b. So adding all those colors together, red for the red channel, green for the green channel, blue for the blue channel. That produces our new image with all those different channels slightly offset differently. And then what we do is we take all this and we blend it with our final result. So let me comment this here. I'll call it combine channels. And then our very last bit will be our output result. And what we're going to do here is we're going to return a mix, so a lerp, of another mix. So we're going to mix our color chromatic, this color channel offset effect, by our block result min, our minimum blocky result, with a percent of 20%, 0.2. And we're going to use that as one image that we're going to blend with our glitch quantize effect with our blurred result, with limiting the colors to 256. And we're going to blend those two things, our chromatic and our blocky result, by our quantized blurred result. And we'll blend those two by 75%. Now you can go in here and start adjusting these numbers, blending different things by blending different things, but I think this will give us something that's pretty good. By overlapping and blending all these different images with different percentages, it's just going to add more kind of blockiness and blurriness and just make it feel more lossy or a lower bit rate. So there's a bunch of other ways you could do these effects, but this is just simply learning three things really. Limiting color depth with quantizing the range, adding blurriness, a very cheap blur or offset, and then adding some blockiness. And then I guess you could also say offsetting some of the color channels a bit. But by doing a couple simple things, now we have something that we can try out. So I'm going to take all this result, throw that back into my material here. See if there's errors. What do we got here? Cannot plus. Let's see what these errors say. Time doesn't exist. Yeah, so it's not a problem with my code. I forgot to add that time variable that we talked about. So you have to go to our custom node here. Add one more input because we're using time within our noise generation here. Use this time noise. So now we have time added. Connect that to a time node. There we go. And we are saving this. And we are going to play this. Okay, so now we have this slight buzzy effect to our screen, like these pink edges that we see on the character. If I go here, let's see if we can get a closer view at that. You see this slight buzzing to the edge of the character. Maybe I'll make it a bit stronger so we can really see that. So I'm going to go here and maybe we blend the color chromatic amount by 0.5. Let's see how that looks. Play. Oh, is that less? I got those flipped around. So 0.1. And now we really start to see that buzzy effect. It's kind of pink offset at the edge of the character. It is subtle, but again, if you want to change the scale of that, our noise scale, smaller numbers will be bigger. So I'll add a couple of zeros. And now you see the whole screen's kind of doing this very kind of wobbly, glitchy effect. And if you really just want to see that one result, like we can always just not output all the code, but just return one thing. And this is very good for troubleshooting. We can just return only our color chromatic. That's just our image with the jiggling color channels. And if we play that, we can just view that and see that glitching effect, right? So now we're blending that with our blockiness result and other stuff and getting the other effects. But that's what it is all by itself. So if you go back and play around with those settings, maybe add a little bit more layers of blur or something, you can end up with something like this, where we really start to get that kind of pixelated, blocky effect, and it starts to feel like really low quality video, or the start of some very low bitrate kind of effect. And in addition to doing our HLSL shader for our post-process, some things you can also do to exaggerate this effect is go into your post-process and start adjusting things like the bloom or the color correction. If you enjoyed this video or you learned something new, don't forget to like and subscribe. Press the bell button to be notified of future videos. And if you are subscribed to the Patreon, which you can find down in the description below, you'll get access to the PDF for all these videos, which will look something like this, which goes over every step we went over in this video in a little bit more detail.